All right, so let me move this down a little bit, get it on all on the same page. So today I'm going to be going over modeling time series. Let me move this over. Um, so I'm going to be going over what is known as Arima models. Arima models have three components to them. The first one is the AR component, which is this auto-regressive time series model. And auto regression model makes an assumption that the observations at previous time series are useful to predict the value at the next time series. It is one of the simplest time series models in which we use a linear model to predict the value at the present time series using the value at the previous time. So if you're trying to predict the stock price of something, Y at T, one way to predict it would be to look at the price of that stock from the previous day. So this would be looking at one previous day. Sorry. This right here is a coefficient, just like in linear regression, we have a coefficient with a time series as well. So this coefficient is is determined same way you do in a time series. You're trying to find a coefficient that will minimize the error function. The order that we select of the AR term, so why don't we do the two previous, if we're doing stocks, why don't we do yesterday and the day previous? So this is a component, this is a number that we need to figure out. In this example, they're just doing one previous day, but you could do two previous days, you could do three previous days, you could do 100 previous days. But when you start adding more features to a regression model, it increases the amount of variance so that it'll start overfitting. So you want to kind of tune this model to figure out how many lag terms to include. So how many should we include? You typically will look at your autocorrelation and partial autocorrelation. So your partial autocorrelation, it really, in this particular model, it really drops off after one lag. So I'd probably start with trying one lag. With the partial correlation, partial autocorrelation, or the pure just autocorrelation. This is autocorrelation, this is partial autocorrelation. So the autocorrelation, we have 4 lags where it's statistically significant, but it kind of just slowly goes down. So you might, I would probably start with 1 lag, see what kind of results I get, and then move on to trying 2 lags or 3 lags or 4 lags. And then we also have the MA component of our Arima model. So there's the AR component, which we just talked about. There's an I component, which we will talk about here in a little bit. And then finally, we have that MA component. The MA component, it stands for moving average. Sometimes a past value is not a useful indicator of what a value will come next. Consider a system that is subject to a lot of shocks and changes. If a previous time period experiences a shock, it may cause an error for future predictions if we just use that value. So a moving average model helps address this behavior. A moving average term in a time series model is a past error multiplied by the coefficient. So it's looking at the one lag past error. You can look at 2 lags past error. A MA model assumes present values related to errors in the past, includes memory of past errors. So yeah. And then finally, there's the differencing term. This is the I component that is in an Arima model. Differencing value is equal to the present value minus the value at the next lag. We do this because the data set is not stationary. So we'll add a I component to it. And then the Arima model, it combines all 3 parts of that. So the AR component, the I component, and the MA component. The differencing value is equal to the present value minus the value at the next lag. A time series which needs to be difference is to be made stationary, is said to be an integrated time series. So that's where the I come from. So yeah. And there's also these three components, they can all have different values for the number of lags you want to include. So the AR current term is typically called a P term. Your differencing term is typically your D, and then your Q is your MA term. So first thing you need to do is you need to plot your data to see if there are trends. If there's trends, we need to remove them because we need stationary data. So you can difference them, you could log transform them, you could do another sort of transformation. If there are seasonal trends, so if there are seasonal trends, then you need to determine how what kind of periods they have. Like, is it seasonal where it's only like the amount of Christmas trees where in November and December that people purchase skyrockets, and then it's completely non-existent the rest of the time. Then you'll typically look at your autocorrelation and your partial autocorrelation. You'll determine the order of differencing for your AR and your MA component if you include both, and then you'll build a model and evaluate it. So we have a data set here. This is on shampoo data. So first thing we're going to do, we see that this data is probably not stationary. Moving average definitely increases, so we need to do some sort of differencing. So after we do some differencing, we see that the data is much more, the moving average stays about the same. It's all around about 0. So then we're going to perform a Dickey-Fuller test. Dickey-Fuller test shows whether the data is stationary or not, a statistical test to do that. We get a p-value way below 0.05, so we can conclude that our data is stationary. This is important to know because we only differenced it by 1 lag and we got it stationary, so that's one of the components for our Arima model. That is the D component. So we know that we need a 1 component in here. So then we're gonna get a autocorrelation. And it plotted twice. If it plots twice, usually if you put a semicolon, it'll only plot it once. Yeah, so plotted it only once. So we see that it is significant after 4 legs. It's still statistically significant. It's outside of this blue area. And yeah. So we're going to do the same thing with partial autocorrelation. And let me reduce this. So this shows that after 3 lags, it's still statistically significant. So what we're going to do then is we're going to try using an Arima model using 3, 1, and 0. And these are all parameters that you need to tune for. You can use these partial autocorrelation and partial autocorrelation as a way to kind of guesstimate where they might be, but you'll still want to tune these parameters and figure out what the optimal parameters are. So if we run this, we get a little summary table. So this is from stats models. All the summary tables are pretty similar. What I'm kind of looking for is, so we have our coefficients for each of our lags. So we have 3 lags because for our AR component. And we see that it's not statistically significant at 3 lags. So that might be something to kind of remember. And then we can plot it. Here's our residuals over time. So nothing crazy pattern-wise. And then our residuals, let's just take a look at it. Are they normal? Are they not normal? They're relatively normal. And then we'll take a look at our prediction. And again, looks like I need a semicolon. And then we can plot or print out the next 36, what the next 36, whatever timestamp this is on, the next 36 inputs. Something I also will like to do is, so we have the residuals, model fit residuals. Let's calculate the mean squared error since we have the residuals. Import numpy as np, np.mean. We want model, what was it, model fit? We want to square each one of these. Oh man, I'm having trouble. So we want to square each of these. So the residual, so the mean squared error on this is 4815. Let's say we take it down to a 210 and see what happens. So still normal for next forecast. So it changes, obviously. So this is, I'm going to put 310 on this. 0. And let's copy this. So this is going to be a 210. So residuals, so the mean squared error did go up a little bit. So it looks like our overall performance didn't improve as much, but I think that everything's statistically significant. Let's do a 311 now. Get a moving average in there as well. And we see that it's the moving average component is not statistically significant either. Now we have a bunch of things that are not statistic. We have 3 features that are not statistically significant. So let's, I just want to kind of see what our mean squared error is. And this is a, I forgot what it is, a 311, I believe. 311. $47.50. So mean squared error went down on that. Let's try a 2-1. Well, I'm gonna try one more, a 2-1-1. I might try a 1-1-1 as well, now that I think about it. All right, so this model did not perform as well as this model. I'm gonna do one more. It's gonna be a 1-1-1. So I didn't really look at this, but these two are not statistically significant. Let's try 1-1-1. So everything's statistically significant. All right. So yeah, this is just one way to kind of compare a bunch of different models and just see how well they do with performance. Later on, I'm going to show you this article on another way to do it a little bit more efficiently. But I want to move on to the next part. So modeling household. So there's another time series that we can play around with. So we're going to fit and evaluate a time series model. So So if you end up watching this recording, I'm going to go through this now, but do kind of try and go through it yourself before before you end up watching how I do it. So first thing I always do, you know, we got to kind of have a cheat sheet here. So plot the data and see if there are any noticeable trends. So we're going to start with that. And what are we wanting to predict? I think we're wanting to global active power. So df dot head df. I want to look at my d types. So this is, the date is a object, so it's a string. I want to convert that. Date equals df date pd.to date time. Cool, so it's a date time now. Date set. I want df. Now I need to set this as the index. Date in place equals true. So we take a look at it now. Now the date is the index. Now I'm going to plot it. Date dot plot time equals line. And I don't want to do date. I want global active power, not date. Global. What is going on? And let's make the fig size a little bit larger. Fig size equals 12 by 8. So it does look like there's some seasonality to it, and it does not look stationary, but let's take a look. Let's test out to see if it is stationary. I don't remember the syntax off the top of my head, so I'm going to steal some code from earlier. Let's steal all of this. And I want df, and I want global active power. And it actually is has a p-value less than 0.05, so it actually is statistically significant. So it doesn't look like we could get away with not doing any differencing on this. There is definitely some seasonality to this, and there's also another type of an Arima model called S-Arima that deals with seasonality like this when the data is still stationary. But cool. So let's. So we don't technically need to do any differencing. So now let's go and take a look at the autocorrelation and partial autocorrelation. And what else did we set on these things? I thought we just set like the lags. So autocorrelation alpha equals 0.05. Alpha. Cool. So it looks like it really jumps down after, oh, I want autocorrelation first. So it looks like a bunch of things are statistics outside of this blue, but it definitely does look like it goes down pretty significantly after like two legs, maybe even 3 legs. Let's do the partial autocorrelation now. So I'm going to do that. And I want this data set now. So yeah, this is what we were looking at earlier, but this really to me says you should really do 2 lags for this. So that's probably what I think I'm going to try. So model equals Arima. I want DF global active power. I need to specify an order. I'm going to try 2, 0, 0. Model fit equals model dot fit. Display equals 0. Print model fit dot summary. All right. My p-values are all statistically significant. We're now going to print out the residuals. PD dot data frame model fit dot resid. And then we want to chain on dot plot that. So there's my residuals. You see that the seasonality does have a little bit of an impact on it, so it's kind of going up and down. So this probably be a good time to do possibly like a seasonal Arima. So now let's do that histogram. I like doing seaborn, so I'm going to do that for histograms. I like doing the disk plot. So very normal. And then finally, let's do the mean squared error. And I want model. And I get a mean squared error of 284,000. I could use that to compare how my different models did. So that's just kind of a basic overview of the Arima model. I have this, when you're doing time series, this machine learning mastery, this person has some really good stuff for time series. And they're all in Python, so I highly recommend this machine learning mastery. And he shows how to, and what you saw earlier probably is I try out a bunch of different versions of this order and see how they compare. I would highly recommend trying to do this with like a for loop, and this guy shows you how to do it. I kind of want to walk through that in the remaining amount of time. So I want to go to the code. So yeah, his first is evaluate Arima model. So, and this takes in the data set and then the order. So whether that's a 310, a 110, and then it applies a training and a test set. And you'll notice that the training in your test set, you hard code what it is. So let me open up a whiteboard. So with typical machine learning, you'll get random subsets. But with a time series, if we take random subsets, it'll look like this. or etc. So all these like empty spots, this would be in our test data set. And if this was what our test data set looks like, this would be pretty easy to predict. It would just go like this, or go like this. It would just, you just connect the lines. But in a real world scenario, when you're predicting like stock price, you wouldn't know the stock price afterwards. After the prediction that you would have, because that wouldn't make sense. You wouldn't need to do a stock prediction. You could just do an interpolation. So with a time series, let me erase all this kind of garbage. I'm just going to go to a new spot. With a time series, what you'll do is, if your time series looks like this, you'll just split it right here. And so you'll train on this, and you'll test on this. So that way you can still do a train test and see how well your model does, but you're not cheating like you are in the other way. So that's what this person is doing right here. He's making 66% of the data, so 2/3 of the data is going to be his train, and then 34% is going to be his test. And that's what he's doing. He's grabbing the first 66%, and then the rest is the test data set. And then what he's doing is doing this step, going through it stepwise. So he's making a, so he takes the training data and he puts it into a list. And then he makes an empty list for his predictions. So what's going to go on here is that for each of his test data sets, he's going to run through a for loop. And each time through the for loop, he's going to run his Arima model, he's going to fit his Arima model, and then he's going to come up with a new forecast for a single element. He's going to add that to the predictions and then append that to his history. So he does that for a single day, and then he's going to run the for loop and then train on everything again, and then just iteratively, step by step, predict things instead of predicting it all at once. It can be a little bit more efficient to do that. Not efficient. You can come up with a better performance that way. Then instead of predicting 100 samples, 100 days, you take all your data, add them one at a time. So it's less drastic of a prediction. What you'll find is that when you make a prediction, you're less confident the farther you go out. But if you train it individually, you're only making a single prediction. So it's usually, it can a lot of times be a little bit less crazy of a prediction. So that's what we're doing. And then, yeah, he writes another function. And in this function, he's going to iterate through all the p-values, all the d-values, and all the q-values, and then put it into that evaluate Arima model. It's that evaluate Arima model returns the mean squared error. And he just sees which one has the best mean squared error. We have the shampoo data set again, and so he's going to try 0, 1, 2, 4, 6, 8, and 10 for your p-values, 0 through 3 for your d-values, and 0 through 3 for your q values. He puts that all in, and then this is the output. So you get each of the different parameters, and then you get the mean squared error. And we see that 4, 2, 1 for this data set gets you the best mean squared error. So we could try it by hand, but doing it programmatically like this is the better way to go through it. So yeah, the project next week is going to be released, and this is a you'll probably want to try tune the parameters on your Arima models, and the project does involve time series. So hopefully this was useful, and have a good rest of the day.